morning. Today we are going to discuss cosmological distances, and the measurement of such distances could be of interest for a variety of reasons. I am going to discuss one possible motivation for carrying out such measurements of cosmological distances. Now, various cosmological models predict different distances for the same redshift. The functional dependence, the functional form on z is of the distance as a, so the distance as a function of z is different for different cosmological models. Now, a point to note over here is that for small z, for redshifts much less than 1, all of them reduce to d is equal to c z by h naught, where c is the speed of light, h naught is the Hubble parameter. And I have discussed a variety of distances, the luminosity distance, the angular diameter distance. The point is that at z much less than 1, all of these distances also match. So, at very small redshifts you have this, at large redshifts you have something else. Now, you could also observe the distance as a function of redshift. So, you have two things, one is the model prediction, other is observation. At small redshifts, redshifts much less than 1, you can compare these two. So, the model predictions all match, they give you this, and you can observe this distance as a function of redshift. So, at small redshifts, redshifts much less than 1, you can compare these two and you can get the value of the Hubble parameter. You can test the Hubble's law, you can test whether the universe is indeed expanding or not, and you can also determine the value of the Hubble parameter. Okay. So, this is what Edwin Hubble, whose picture is shown over here, this is what he had done originally. He had determined the distances as a function of redshift. Here it is shown in slightly different units. So, you have velocities and distances, but it is essentially the same thing, and he had found a linear relation from where he had obtained the value of the Hubble parameter. Now, there are several problems that have to be overcome before you can get a reliable estimate of the Hubble parameter, and the estimate which Hubble had got was quite high, too high actually. It was around 500 kilometers per second per megaparsec, and one of the problems was that the age of the universe implied by this was incorrect, was too small. There were objects already quite comparable to that age. Right, inverse of the Hubble parameter gives the age, we have discussed this. So, let me tell you about one of the problems that interfere with the determination of the Hubble parameter. So, to determine the Hubble parameter, you have to determine the distance and the redshift and then compare these two, right, separately. You have to determine them independently. Now, this is perfectly fine if all the galaxies, the only motion of the galaxies, all that the galaxies do is that they move apart from one another with the expansion of the universe. But that is not true. Galaxies have motions in addition to that predicted by Hubble's law. These velocities are referred to as peculiar velocities. So, Hubble's law for a certain distance, consider a galaxy at a certain distance, Hubble's law would predict that it should have a certain redshift, a certain redshift. It should be moving away from the observer. So, I am sitting here, I observe a galaxy at a certain distance. Hubble's law predicts that it should be moving away from me with a certain redshift, velocity. For small redshifts, I can interpret it as velocity. But galaxies, in addition to this Hubble expansion, they have their own motions. These motions as we shall discuss later, are determined by the local gravitational field. So, the universe is not exactly homogeneous and isotropic. I have shown you pictures, and in these pictures you have seen that the universe is not exactly homogeneous and isotropic. It is so, it approaches homogeneity and isotropy as you go to larger and larger scales. But on small scales, on scales of megaparsecs, tens of megaparsecs also, there are fluctuations. Somewhere you have more galaxies, somewhere you have less galaxies. Okay. And the regions where there are more galaxies, they will exert an extra gravitational attraction on these galaxies near it. And region where there are less galaxies, they will exert a kind of repulsion away from it. Okay. So, these introduce extra motions in the galaxies. And I had shown you a picture, if you remember, where there was a man in the sky. That pattern, we were seeing the redshift interpreted as distance. There we did not have direct distance estimates, only redshift, which we interpreted as distance, and we saw that we got this very strange pattern. That was essentially due to these peculiar velocities. So, peculiar velocities are very important, and they are, it has been observationally found that these peculiar velocities are of the order of hundreds of kilometers per second, maybe up to 1000 at most, of that order, 100 to 1000. Okay, maybe less also, but they are of this order, okay, hundreds of kilometers per second. So, just to make an estimate, I have assumed that the peculiar velocity, this is not the Hubble velocity, but the peculiar velocity is of the order of 300 kilometers per second. So, if a galaxy has a peculiar velocity of 300 kilometers per second in the nearby universe, then this would introduce an extra redshift V by C, which is of the order of 0.0. So, we have to divide by C, which is 3 into 10 to the power 5, this is 3 into 10 to the power 2. So, we have 10 to the power minus 3 as the contribution from peculiar velocities to redshift. So, this gives an order of magnitude of the contribution from peculiar velocities to the redshift, which is of the order of 10 to the power minus 3, maybe slightly more, but of that order. Okay. Now, if you carry out observations in the very near universe and you want to determine Hubble constant, then the peculiar velocity can possibly potentially can make a significant contribution. So, if you want to keep the uncertainties due to the peculiar velocity to less than 10%, so you have to go to a redshift where the Hubble redshift is 10 times this. Right? If the Hubble expansion redshift is 10 times this, then the errors that can be introduced due to peculiar velocity will be less than 10%. Okay. Which tells us that you have to go to a redshift of 0.01, 10 times this value, or you have to look at distances, you have to consider galaxies at distances which are 0.01 into C by h naught, and I have taken h naught to be 100 here. So, this gives an estimate of the distances where I have to look if I want to get a reliable estimate of the Hubble parameter. So, I would then have to look at distances greater than 30 megaparsec. This number could be larger if you have slightly larger contributions from peculiar velocities. It could also be larger if the Hubble parameter is smaller. I have used 100. Okay. But this gives some typical number of the length scales that we have to look at. So, we have to consider length scales not within tens of megaparsec, but of the order of 50, 100, few hundred megaparsecs to get a reliable estimate of the Hubble parameter. Smaller redshifts, there are going to be large uncertainties due to the peculiar velocity. Okay, the contribution from peculiar velocity is going to get smaller and smaller as you go to larger and larger redshifts. Right, this is going more or less constant, 10 to the power minus 3, but as you go to larger and larger redshifts, this becomes a smaller and smaller fraction. So, that will introduce a smaller and smaller uncertainty in the Hubble parameter. Okay. And if you want the linear relation to hold, then you have to be in the range where z is much less than 1. So, it gives you an idea of where you could carry out these estimates. So, you have a considerable range of redshifts where you could carry out such estimates. Okay. Now, this was at low redshifts. If you can carry out observations, same observations, that is, you get the distance independently, get the redshift independently at large redshifts. So, redshifts 1 or larger. At these large redshifts, the model predictions depend on the cosmological parameters. They are different for different cosmological models. We have discussed this in the last class. So, if you have a model where you have 3 parameters, omega matter naught, omega curvature naught and omega lambda naught, for example, then the distances depend on the choice of these values of these parameters. They are quite different. And you have again different kinds of distances, the angular diameter distance, the luminosity distance, etc. So, if you have independent observations and theoretical predictions, then you can compare these two and put constraints on the allowed value of the cosmological parameters. You can actually use these observations to determine what is the cosmological model that we actually are living in. What are, so you can first address the question, can our universe, can the constituents of our universe be adequately parameterized by just these 3 parameters, just 3 constituents which are parameterized by these 3 numbers, or do we need more? If you find that fine, this gives an adequate description, then what are the values, allowed values, what is the range of values for which you can have adequate description of the observed universe. Okay, so you can use distance measurements to do this. So now the question arises, how do you determine distances? You have to determine distances out to large scales. In an earlier lecture, I had told you how you could, one method, I had discussed the cosmic distance ladder. So, in our earlier discussion, we had started from the solar system and then we had gone out to our galaxy, within our galaxy, and then we had gone slightly beyond our galaxy, how you can determine distances to nearby galaxies. Now, here we would like to determine distances for objects more than 30 megaparsecs, right. That is where you will get reliable estimates of the Hubble parameter, hundreds of megaparsec, tens to hundreds, okay, few tens to hundreds. And obviously, you cannot suddenly go in one step, jump from to determine the distances of such large objects. So, as I had explained you earlier, we have this distance ladder where you have overlapping distance ranges where you can use 2 methods. So, one method, for example, we start with the solar system and then we have parallax, and then we had told you about the fitting the cluster star distribution in clusters to the HR diagram. So, if you have overlapping regions, you can use them to calibrate one method against the other. So, in this way you can build up a distance scale which extends to larger and larger length scales. Okay. So, we are going to discuss this, the cosmic ladder. So, we are going to extend it further. We have gone up to the Cepheids in earlier lectures. Okay. So, we will start with the large scales, tens and hundreds of megaparsec. Now, let me go over this point by point. First point is that at these large scales, tens and hundreds of megaparsec, you cannot identify individual objects inside galaxies. We had discussed about Cepheid variable stars which have a period luminosity relation. Now, for such distant galaxies, the galaxy just appears as a hazy bright region. You cannot make out individual stars or individual objects inside these distant galaxies. Okay. So, you do not have the luxury of using Cepheid variables or such things. Okay. So, what you have to do is that you have to use the properties of the entire galaxy as a standard candle. or a standard ruler. I have told you what is a standard candle or a standard ruler. A standard candle is an object whose luminosity is known, right. A standard ruler is an object whose length, physical dimension is known. So, wherever you place it, you know that it will have this size. So, you have to use the galaxy itself as a standard candle or a standard ruler. Okay. You cannot, the properties of the galaxies have to be used to construct standard candle and standard ruler. You cannot use the galaxy luminosity itself as a standard candle. The galaxies come in different varieties, even elliptical galaxies or spiral galaxies, they come with a range of luminosities, not that they all come with the same luminosity. So, I cannot use I cannot just make an assumption that I am going to use the galaxy's luminosity as a standard candle. I am going to assume it has a fixed value and go ahead. No, that does not work. It will give, there will be a large scatter in the luminosities, and this will again introduce uncertainties in the value that you get for the Hubble parameter or the cosmological parameters. You will not be able to make accurate estimates of these parameters because the luminosity is uncertain. Okay. So, you cannot directly use the luminosity or the size of galaxies as the standard candle or ruler, but what you can do, what can be done and what is done is that people have found correlations between different properties of the galaxy, between different galaxy properties, measurable galaxy properties, and these correlations allow us to construct standard candles or standard rulers. So, if you have different quantities which you can measure, which are correlated to the luminosity or the size of the galaxy, then you can use these to construct standard candles or standard rulers. That is the basic philosophy. So, let us start off with discussing elliptical galaxies. This shows you a picture of an elliptical galaxy. I had mentioned this, I had introduced elliptical galaxies way back in the first or second lecture. This shows you a picture of an elliptical galaxy. So, we have stars which have an ellipsoidal distribution, and just look at this elliptical galaxy. In this picture you cannot make out any individual objects, right. It is a bright, what you can see is the brightness, the distribution of the brightness. Okay. So, this brightness distribution is described by what is called de Vaucouleurs law. It is an empirical finding. De Vaucouleurs r to the power 1/4 law. So, before telling you what the law is written over here, before telling you this, let me first discuss, very briefly discuss how we quantify this surface brightness. So, this is a very important concept, and today I will just introduce it. I will not discuss its properties. In a later lecture, as we require it, I shall introduce some of the properties of the surface brightness. So, the surface brightness is quantified as follows. Consider an area dA, infinitesimal area dA. So, think of so you are trying to detect the radiation. The basic issue is that you want to quantify the radiation coming from this object or coming somewhere, okay, from a certain direction. So, what you do here, in any radiation detection, you will have a detector which will detect the amount of radiation coming. Okay. So, here we have a detector of area dA, infinitesimal detector, and the detector is sensitive to radiation in the frequency range d nu, and it measures the amount of radiation coming in a time interval dt. And the detector that we consider over here is not sensitive to radiation in all directions. After all, you want to know the angular dependence of the brightness. So, the detector over here is only sensitive to radiation from a particular direction. So, the detector that we are considering over here, that I have shown in this picture over here, is sensitive to radiation coming in the normal direction, and it is sensitive not just to radiation in a single direction, but in a small range of solid angles around this. So, this detector is going to detect all radiations coming with a solid angle d omega. So, what the detector is going to give you finally is the amount of energy that comes per solid angle, or in that solid angle d omega, in that area dA, in a time interval d nu, in a time interval dt, in the frequency interval d nu. So, this energy is written as I nu, the specific intensity or surface brightness, into all of these factors. This is the specific intensity is what quantifies the brightness, surface because per solid angle, right. So, it is essentially the flux, the specific flux plus solid angle. Okay. So, this is what we use to quantify the brightness. And what Dweck found, Dweck's law, r to the power 1/4 law says, is that this surface brightness or specific intensity, here it is expressed as a function of r, not as the direction, but r. R could be easily converted to direction, because if I point towards the center here, that will be r equal to 0. As I move away, the r will change, the direction also will change. Okay. So, the specific intensity as a function of r is the distance from the center of the galaxy, can be expressed as I naught exponential minus r by r naught to the power 1/4. Okay. This is what Dweck found for the brightness of the elliptical galaxy. Now, another thing that we need about this elliptical galaxy is that the stars in this elliptical galaxy have random motions, and the galaxy is supported against collapsing because of the random motions of these stars. If the stars were all at rest, they would collapse to the center because of the gravitational attraction. So, they have random motions which keep the whole shape of the elliptical galaxy intact. The random motion, the kinetic energy and the potential energy, they are balanced and it is a random motion that is maintaining the shape of the galaxy, this galaxy in equilibrium. So, you have the stars in the galaxy have a velocity dispersion. Random motions can be quantified by the velocity dispersion, sigma v, and the velocity dispersion could be different for different parts of the galaxy. So, sigma v is the velocity dispersion at the center of the galaxy. So, you can measure sigma v straight away, provided, so if you can get the spectrum of the galaxy, the velocity dispersion will get converted into the width of the spectrum, and you can determine this from observations, and that does not change with distance. It will get contracted or expanded due to redshift, but you can easily correct for that because the redshift is measured. We have a galaxy, we have measured its redshift, we can measure its velocity dispersion, correct for redshift. Okay. The specific intensity has this very interesting property which I am not going to prove right now, I will prove it later. It has the property that as a light ray propagates, if there are no absorption, if there is no absorption or emission in between, then the specific intensity remains conserved. Okay. As a light ray propagates, so the light from the sun as it propagates to us, the specific intensity remains, the surface brightness remains unchanged. Okay. It has this very interesting and useful property. Now, in the cosmological context, there is one more effect, that is the solid angles get changed. Okay. Not, you have to take into account the solid angle correctly, and the frequency essentially gets changed. That is a big difference. Okay. So, if there is no change in frequency or anything, then the specific intensity is conserved, but because of the change in the frequency as the light propagates from a distant galaxy to us, there will be a change in the specific intensity, but that again depends on the redshift, does not depend on the distance, just depends on the change in the frequency of the photons. So, you can correct for that. So, you can directly observe the specific intensity and the velocity dispersion, and you can determine okay, so you can determine these two directly from observations, but you cannot determine the luminosity, because total luminosity, because that will change as with the distance. As you put the galaxy further and further away, the luminosity is going to be different, okay, but the specific intensity does not change, surface brightness does not change. Okay. The total luminosity can be calculated from the specific intensity by integrating over all the solid angle. The galaxy is going to subtend a certain solid angle, right. So, if you integrate over that, you will get the total, you will not get the total luminosity, you will get the flux coming to us, okay, which is related to the total luminosity. Okay. Now, I had mentioned that you have to look for correlations between different observable quantities. Now, it has been found observationally that there is a correlation between the galaxy's luminosity L, the value of the specific intensity at the center of the galaxy I naught, and the velocity central velocity dispersion sigma v. Okay, it has been found observationally that there is a correlation between these, and the luminosity is proportional to the central surface brightness to some power and the sigma velocity dispersion to some other power, where these powers are given over here, and this is called a fundamental plane relation, the fundamental plane relation. Why is it called the fundamental plane? Because you have a 3-dimensional space now, L, I naught and sigma v. In this 3-dimensional plane, the galaxies are all found to lie in a plane, in a 2-dimensional surface, which is given by this. Okay. Now, this can be, it can be understood on physical grounds how this comes about. Okay, but I shall not go into that over here. So, if you can determine I naught and sigma v from observations, you can then get the luminosity. Okay. But the problem is that to determine the constant of integration, this constant of proportionality, not integration, to determine the constant of proportionality, there should be some galaxies all at the same distance, or there should be a large sample of galaxies for which all three are known. Only then can you get the constant of proportionality. Okay. And if you want to get the luminosity, then the distance should be known. So, you should have a large set of galaxies for which the distances are known. Okay. Now, that is the difficult part. So, what happens is that suppose you have you find a set of galaxies which you believe are at the same distance, roughly the same distance. Then what you can do is you can establish that such a relation exists, but since you do not know what the distance is, you know that the distance is same, but since you do not know what the distance is, then the constant of proportionality remains unknown. It remains an unknown constant, because I do not know the luminosity. What I can measure is the flux. Okay. But I can say that for all the galaxies, the flux and luminosity are related in exactly the same way, because they are at the same distance roughly. Okay. So, if I do that, I can establish that there is such a relation between luminosity and these two things, but I cannot determine the constant of proportionality. Okay. This is something that you have to bear in mind. Okay. So, the constant is not really known, it is an uncertain, it is some number, okay, but it is a constant, this to a large, okay, the tight correlation exists between these three things. There is another similar relation which is called the dn sigma relation. Okay. What is dn? Now, this is the galaxy, and you can identify a diameter for the galaxy, right. And as you increase the diameter, the surface brightness, the mean surface brightness within that is going to fall, because the surface brightness is falling with distance, right. So I can draw an ellipse or aligned with this, and if I make it larger and larger, the mean surface brightness is going to fall, okay. But then the diameter is increasing, so the surface brightness inside, average surface brightness is falling. Now people have found that if you vary, so you can vary the, you can ask that what is the diameter which subtends such that the mean surface brightness inside has a particular value, okay, and you can vary this value, you will get a different diameter. People found that for some suitable choice of this threshold value, there is a relation between the diameter and the velocity dispersion. Okay, so this is the diameter of the galaxy defined in some way. Okay, if defined correctly, you find such that the mean surface brightness has a particular threshold value. For a right choice of the threshold value, people have found that there is a relation between this diameter of the galaxy and the velocity dispersion. Velocity dispersion can be measured directly. So if you can measure this, you get the diameter. Okay, again here unknown constants come in, same reason as this. Okay, so it is constant, it is a constant for all galaxies, but we do not know what the constant is. So you cannot determine the distance, you can get proportional. Okay, I will come to this issue again. There is also the Faber-Jackson relation. The Faber-Jackson relation, it is again an observational finding, and what Faber and Jackson found is that the luminosity is proportional, the galaxy's luminosity is proportional to its velocity dispersion to some power alpha, and the values of alpha are not arbitrary, they are in a range 3 to 4. Okay, there is a scatter, but in a range 3 to 4. This is the Faber-Jackson relation. Okay, so if you can measure the velocity dispersion of an elliptical galaxy, you can predict its luminosity. Now the fundamental plane is a tighter relation, the correlations are stronger, this has a larger uncertainty. Okay, so if you measure this, you cannot say with great certainty that the luminosity is this value, because there is a spread in the value of alpha. Okay, but it will give you some estimate of the luminosity. Now for spiral galaxies, you have a similar thing. I have discussed spiral galaxies at greater length than we have discussed elliptical, so I am not showing you a picture. I have told you that from various observations, particularly 21 centimeter observations, we know that spiral galaxies are supported by rotation, and they have a flat rotation curve beyond a certain distance. So there is a rotational velocity. Now there is a Tully-Fisher relation very similar to the Faber-Jackson relation. So this was discovered by Tully and Fisher, two astronomers, and they found that the rotational velocity is related to the luminosity of the galaxy. Okay, so if you know the rotational velocity, you can predict the luminosity. And the luminosity could be measured in optical, or it could be measured in the infrared, or in the 21 centimeter band, and you will get different Tully-Fisher relations for all three of these. But the basic point here is that if you can measure the rotational velocity, you can then use the Tully-Fisher relation to predict the luminosity. Okay, you cannot determine the luminosity directly, you can measure the flux. So now if you know the luminosity and flux, you can determine the distance, right. Luminosity you can get from this Tully-Fisher relation, flux you can measure, so if you know both of them, you can get the distance. That is the basic idea. Okay. Now if you use galaxies as standard candles, the problem is that there are 20% or more, around 20% scatter. Okay, so you measure, just for example, if you measure the velocity, rotational velocity of a spiral galaxy and use that to predict the luminosity, then you will find that for the same rotational velocity, the luminosities will not always come out to be exactly the same value, there will be a 20% scatter. Okay. So there is an uncertainty of 20% in the value of the luminosity, and if you use this to determine the distance, then there will be a corresponding uncertainty in the distance, which will be reflected again in the Hubble parameter. Okay. So, you cannot use these galaxies as standard candles, individual galaxies as standard candles to get reliable estimates, very reliable estimates of the Hubble parameter. What you can do is that you have to, if you can find many galaxies together in some region and you have reason to believe that these galaxies are physically associated and are at roughly the same distance, then you can use the distance estimates from all of these galaxies. If you have many independent estimates, the error goes down. Okay, that is an important fact. So, if I have many independent estimates, each of them has some error, then if I combine all of them to get one single estimate, then the error goes down as root of n. Okay, that is a point we shall come to later. So, this is what is done. So, it has been found, it is an observational fact that the galaxies are not absolutely uniformly distributed on the sky on all scales. So, on sufficiently small scales there is a clustering pattern, and there are objects called clusters of galaxies. So, this is a picture of a particular cluster. Okay. So, here you find a large number of galaxies. So, these are galaxies, many large number of galaxies in a very small region. Okay. And these galaxies are gravitationally bound. So, they are gravitationally bound, just like the sun, earth is gravitational, the sun earth is a gravitationally bound system. Similarly, these galaxies are a gravitationally bound system called a cluster of galaxies. Okay. And I cannot think of, so it would be wrong if I thought of these galaxies all moving away from me with the Hubble, according to Hubble's law. No, the cluster is now to be thought of as moving away from me according to Hubble's law of expansion. And the galaxies have got considerable peculiar velocities, which is because they are bound inside this gravitationally bound object, a cluster of galaxies. Okay. And the size of the cluster is of the order is of few megaparsec size, and there could be as many as 1000 galaxies inside a cluster of galaxy, but most of them are extremely small galaxies. Okay, extremely small galaxies. I have okay, clusters. I have told you that there are mainly ellipticals inside clusters. Okay, ellipticals. So, inside clusters you mainly find ellipticals. You do not find spirals. Okay, you may find a few towards the outer part of the cluster, but usually you do not find many spirals. Okay. Now, the Coma cluster and the Virgo cluster are two of the nearest clusters, two clusters which are nearest to us. The Virgo cluster is actually the nearest cluster. So, it is the nearest cluster nearest to us. It is a rather diffuse cluster. It is not clear whether it is still, it is already, it is completely relaxed or it is still in the formation process. It is not very clear. It is a cluster of moderate richness, not a very rich cluster. So, the richness depends on the number of galaxies, bright galaxies in the cluster. So, it is a relatively moderate, it is of relatively moderate richness. Okay, but it is the nearest cluster, and the Coma cluster is the nearest cluster of the richest class. Okay, so, it is the nearest very rich cluster. So, these are the two clusters which are near us, and what people have done is that they have used these two clusters. So, they have applied the dn sigma relation to these two clusters. Now, the Coma cluster redshift is z equal to 0.02, and it is sufficiently far so that you can use it to get a reliable estimate of the Hubble parameter. Okay, if it were nearer, then the peculiar velocity would be considerable and you would not be able to use it to get a reliable estimate of the Hubble parameter. So, the coma cluster is sufficiently far so that you can use it to get a reliable estimate of the Hubble parameter. Now, the dn sigma relation has been applied. I am just discussing a particular set of observations, and there are other. So, this is a large observational project to determine distances. I am going to discuss only a small part of these observations. Okay. So, the dn sigma relation has been applied to both of these clusters. So, it has been applied to the coma cluster, it has been applied to the Virgo cluster. So, this gives us the angular diameters of these galaxies. So, you know the size, you can measure the angle subtended by these galaxies in these clusters, and this gives estimates of the distances to these clusters. Okay. So, you can assume that the galaxies inside the cluster are more or less at the same distance. Okay. Now, as I had told you, there are constants of integration whose values are not known, right. So, from these observations what you can do, you can determine the ratio of the angular diameter distance to coma and Virgo. You cannot tell what these values are, okay, but you can get the ratio of the distances to the coma cluster and the Virgo cluster. Okay. And since the redshift of the Virgo cluster is known, you can use this to determine Hubble parameter in terms of the distance to Virgo. Okay, and that gives h to have this particular value. So, now the distance to Virgo is uncertain, but there is a big step that has been made. If I had used this coma cluster, then the distance to coma would be uncertain. Now, that uncertainty has been, the unknown has been changed from the coma distance to the Virgo distance, and Virgo is nearer. So, the whole thing is that to slowly get nearer and nearer till you get to a region where you know distances from other means. Okay. So, by using this method, the dn sigma relation, it is possible to determine the distance to the coma cluster in terms of distance to the Virgo cluster and get an estimate of the Hubble parameter. Now, so that was at large scales. At intermediate scales, there are two methods that can be applied at intermediate scales, which I am going to discuss. There may be other methods, but I am not going to discuss them. The first method is that you can determine distances through brightness in the surface brightness fluctuations. Let me explain this method to you. So, you are observing a galaxy. This is the galaxy, and the observer is sitting over here. And what the observer measures is the surface brightness. So, he will have an instrument, the instrument will have some resolution, and what the observer is going to measure is the surface brightness. So, this is the solid angle delta omega, right, and the observer is going to measure the amount of radiation coming inside this, all other things delta t, delta nu, dA, delta A being constant, same. Okay. Now, this is a galaxy, and we know that galaxies, the light in galaxies comes from stars. So, there are discrete stars inside this. The number of stars over here, the mean number of stars in this that contribute to the radiation coming in this solid angle, n is equal to the number density of stars, which you can take to be roughly constant inside the galaxies, surface per unit area, how many are there, into the area subtended by this solid angle, right, and that is going to be d angular square into delta omega. Okay. Now, if I have discrete objects, like stars, right, so this gives me the surface brightness is proportional to this. Not the surface brightness, sorry, the surface brightness then is essentially proportional to d, or okay, the number, forget about this, the number of stars that are there in this solid angle is proportional to this. Okay. And the solid, so we are going to observe galaxies at different distances. Okay. So this is another galaxy. So this is a same solid angle, but at a different distance. So the number of galaxies in this, number of stars inside this region is going to be larger, because this d square is larger. So the further away the galaxy is, the same solid angle, there are going to be more stars. Okay. Now consider the situation where I take this beam and put it at different places on the galaxy. Each time I put it somewhere, I am not going to get exactly this number, there will be fluctuations, that is called the Poisson fluctuation. So whenever you have discrete objects and you sample it, there will be fluctuations called the Poisson fluctuation. You might have encountered it in this nuclear physics experiments when you count the number of gamma particles or whatever beta particles that come out in a time interval. Okay. So the Poisson fluctuations are going to be proportional to so the fluctuations are proportional are actually equal to the square root of n. Okay. And in the continuum limit, when n becomes very large, there will be no Poisson fluctuation. Okay. So if I have n discrete objects inside this beam that are contributing, then there will be a fluctuation root n. Okay. So this fluctuation in the number of stars is going to get translated to fluctuations in the specific intensity, and these are proportional to square root of n. So this is proportional to the fluctuation. So the what you can actually measure is the fractional fluctuation is what is of interest, right? By what fraction does it vary when I move it from one point to another, and that varies like this. So this is proportional to 1 by square root of n. So by what fraction does the specific intensity vary if I move the beam around to different parts of the galaxy, and this goes as 1 by square root of n, or it goes as 1 by the angular diameter distance. Okay. So you can use this to determine the angular diameter distances to galaxies. But again, so what are the restrictions now? The restrictions are that the galaxy should subtend a sufficiently large angle to get the variance, and the second point is that that's the main restriction. The galaxy should subtend a sufficiently large angle for you to be able to determine these, get many angles, many solid angles, otherwise you will not get a variance. And the second point is that the constant of proportionality is unknown, because the distances to these galaxies you have to determine by some other means to be able to get the constant of proportionality. Okay. The other method which can work over here is through planetary nebulae. These are gas envelopes which are expelled from very massive stars, okay, very bright, and these, the maximum luminosity of these gas envelopes is known, so they can be used as standard candles, okay, and you can identify them. They have strong emission lines, so you can identify them inside galaxies. So here again the galaxies, you cannot make out individual objects, but you can use these two things as standard candles, and the uncertainties are of the order of 5%, and these two methods can be applied to galaxies in the Virgo cluster. They can also be applied to M31, which is a very nearby galaxy. okay, and they give, so you can now reduce the problem to determining the distance to M31. Now the distance to M31 can be determined using C-feed variables, which we have already discussed, okay. So you can use this to get the distance to M31 in terms of the distance to the Large Magellanic Cloud, a nearby dwarf galaxy, satellite of our galaxy. So in both M31 and this you can identify C-feed variables, okay, they are sufficiently near so that you can identify stars in these galaxies, and finally you are led to a value of the Hubble parameter which has this value, okay, this value. So I have discussed one set of observations and which and the value finally arrived at. Now this shows you the Hubble diagram. So I had discussed the Hubble diagram, right, velocity as a function of redshift, as a function of distance. So this is a modern Hubble diagram based on these techniques that I have mentioned, okay. So this is a modern Hubble diagram based on these techniques that I have discussed, and you have all of them, all of these techniques, data obtained from all of these techniques plotted over here. You have the Tully-Fisher relation, you have the fundamental plane, and then you have the surface brightness fluctuations, and then you have supernova, which I am going to discuss in the next class, okay. So the three things that I have discussed, they are all restricted to relatively small distances of the order of 100, maximum going up to 200, okay, over here, and you can use these to get estimates for the Hubble parameters. So these are the estimates of the Hubble parameter that you get from these values. They are around 70, okay, somewhere around 70, so varying around 70, okay. So let me stop here for today. In tomorrow's class we are going to continue this discussion and discuss supernova 1A observation, supernova observations.